I'm the manager of corporate analysis here at Wolfram Research, and I'm here to talk to you about business intelligence using Mathematica and CDF. So let's get started. What is business intelligence? So business intelligence is a process. It's the process by which we create knowledge. We create knowledge from raw data by analyzing it and by mining it. And when I say knowledge, I'm talking about a true understanding of the behavior of our customers. If we can understand the behavior of our customers, then we can discover opportunities and we can implement strategies in order to take advantage of those opportunities. Now, business intelligence is actually a cyclic process because once you have implemented some sort of strategy, you have to go back and see how well that strategy is working. And so you have to go back, mine more data, turn it into knowledge, and develop even newer opportunities. So I'd like to set the stage. I would like for all of us to get into the analyst's mindset. So I'll try and do this as a story. Today's technology landscape is pretty diverse. There's lots of technology out there. When I was at Hadoop World last year, outside of the conference rooms, the hallways were filled with vendors of people selling all kinds of BI technologies that promised to solve all of your BI questions. But ultimately, this is just marketing, because the most important thing in BI is intelligent people. It's intelligent people that have to analyze the data. It's intelligent people that have to find the correlations between things. And it's intelligent people that have to ask the questions, right? So as analysts, we actually need to be adaptable. We need to be adaptable to our business because our business will have its own set of metrics, right? And we also have to be adaptable to the set of technologies that are out there because no business is the same and no business uses the same technology. And so we start by asking the questions and we explore the answers. So I'd like to go a little bit now through the BI process as a step-by-step thing. The first step in a BI process is to determine what it is we want to measure. I work in web intelligence, and so we try to infer our customer behavior from things like web statistics. And these are very standard things that are well-defined: page views, unique users, popularities. Ultimately, though, we are trying to engage our customers because the more we engage them, the more money we can make from them. The second step in a BI process is to summarize your data. The data needs to be easily accessible by people. And so we summarize our data using various technologies. Some of the open source ones are things like Hadoop and MySQL, and that's what we use. But there are also commercial tools like Oracle and MS SQL that can do the same thing. The most important thing is that the data be easily accessible. If you can't access the data, you can't answer any questions. And the other thing is, the data should be accessible by anyone who can ask a question, not just analysts, because there's usually very few of us. And if we can push the data out to the people who are asking the questions, then we don't have to do as much work. The third step in the BI process is to analyze the data to find patterns. Because data tells a story. And so you have to ask yourself this question. When you're looking at the data, is it telling you a story? Because if it isn't telling you a story, then it's not that useful. So the process of analyzing the data involves cleaning it, turning it into something that will tell a story, so that it can answer questions like, where did that spike come from? And did this campaign have an effect on traffic or on sales? Now, if you're looking at your data and it's not answering the questions, then it means you need to go back, maybe to step 1, maybe to step 2. Summarize new things, figure out new things that you want to measure, start the process again, explore. So now I'd like to talk a little bit about the BI stack. The BI stack is it's basically the technology that we use to do analytics. And it should be tailored to your business's needs. When I say that, I'm really talking about the notion that some businesses will generate more web traffic than others, and if you're generating large amounts of web traffic, then you're going to need a large amount of computing power. But if you're not, then you don't need to throw all of that stuff at it. You can use less technology and save time. So at the core of any business intelligence is what I like to call the standard architectural stack. And so the bottom of the stack we have data warehousing. In data warehousing, that's the component of the stack where you store data. You keep it in a central location. Sitting on top of data warehousing is data processing. And there's many tools that can do data processing. Simple things like MySQL actually is a data processing tool. Once you've loaded it into MySQL, you can run queries. That's a transformation. Then, sitting on top of the data processing step is the analytics. This is where the intelligence starts. This is where you do your data mining. This is where you do your statistical analysis. This is where you find correlations. When you've done these things, it becomes possible to identify metrics that we can use to measure and determine whether our business is doing what we want it to do. And we can visualize data to see if it's been doing well in the past and how it's going to do in the future using projections. So at Wolfram, in Web Intelligence, we use Hadoop and MySQL for our data warehousing needs. And we use Dumbo and some MySQL as well to do the data processing. Now, a tool that's very frequently forgotten is the tool that coordinates the whole thing. And I wanted to mention it. We use a tool called Jenkins, which coordinates our jobs and schedules everything. And then we have Mathematica. We use Mathematica for doing our analytics, and for doing reporting, and for doing visualization. And so Mathematica actually fits in the top two components of the stack. So in business intelligence, we typically have this thing called a data pipeline. The data pipeline is basically the process that brings everything together. Ultimately, in order to do analytics, your data needs to be in a center, in a single location. And so in Web Intel, what we do is we download our Apache logs from Wolfram Alpha and from other things all into a central location using standard open source tools like rsync, for instance. Now, once all of the log files are in a single location, we upload them into our Hadoop cluster, HDFS, Hadoop's distributed file system. Now, the data used for business intelligence isn't only in the Apache logs. There is also very important information in other databases, like, for instance, subscriber information for Wolfram Alpha Pro. When you tie in subscriber information, you get new insight into what users are doing. And so we also need to bring that data into a central location as well. So we make snapshots of the Wolfram Alpha databases, and we copy them into a local instance, a local MySQL instance. Now, once all of this data is in a central location, we create summary data, like page views and unique users, and we do this using Dumbo. Now, as I mentioned before, businesses have their own set of metrics. And so we use Dumbo to compute our metrics as well, the ones that we find interesting and important. Once all of this data has been summarized, we load it into our corporate analysis MySQL database or HBase where appropriate. Once all of the data is in a central location, we can now load it into Mathematica. And as Todd Galey said right before me, Mathematica provides great tools for accessing data from a very diverse set of sources. Once you've loaded this data into Mathematica, though, it's not yet telling a story. To get it to the point where it's telling a story, we have to first normalize it. When you normalize your data, you provide visibility on the useful information. This helps us to infer the real knowledge that the data is telling us. Now, once you've created something that's telling a story, you don't want to just lose it. You always have to keep sight of it. And so we institutionalize this data by automating the process that creates it. So this has all been very hand-wavy. I'd like to now go into a little walkthrough where I actually show an example of a simple report that we did back in May. Now, there are two types of analytics. There's question and answer, and then there is exploratory. Now, the thing about analytics and these two types is that they have a somewhat symbiotic relationship. When you ask a question, you need to explore in order to find the answer. And in the process of exploration, you will discover new questions to ask. And you will ask them, and you will answer more questions. And so, hopefully, in your analytics, you end up in a nice process where you're constantly asking questions and searching. So, back in May, I was asked, has the number of computation timeouts increased since the release of Wolfram Alpha Pro? Now, before you do any analytics, we need to ask ourselves why. Why do you want to know this? Now, the reason we ask why is not because we don't want to do any work. It's because by asking the question, it can lead to insightful ideas, and it can also lead to the underlying questions, which are the real questions that people are asking. Very frequently, when people ask for a report, they're not asking, they think of what they want to know, and then they ask it, or they phrase it in a way that actually obscures the original intent. And so you have to ask why to get to the real golden nugget. Once you have that, then you can answer the real question. Now in this case, when I asked why, I found out that we had received complaints from customers that the number of computation timeouts had increased since the launch of Wolfram Alpha Pro. So the facts are that Wolfram Alpha Pro was launched on February 8th, 2012. And we should be able to count the number of computation timeouts if the computation timeouts occur in our logs. And so first we need to identify that it's in the Apache logs. So step one, let's take a look to see if computation timeouts occur in the logs. In order to do that, I went ahead and I used Google Chrome to execute a computation on Wolfram Alpha, the Fourier transform of the square root of sine of x over log x, which is something I never had to do in school, thankfully, because I don't think it's not easy. In Mathematica, it takes forever. So you execute this thing, and if you open up the developer tools in Google Chrome, and you go to the network resource tab, you'll see that a request is made to timeout.jsp. Now the important bit here is /calculate/timeout.jsp with the argument compto equals to true. So when a computation timeout occurs, a request to timeout.jsp is made. And sure enough, I went ahead and I opened up the log file on our servers, and I did a search for timeout.jsp, and it's there. I think it's actually a bit too hard to see, but it's not that important. So we now know that it's there. So that means we can count it. Now, because we generate such a large amount of traffic at Wolfram, we typically have to do our counting with MapReduce. Now, if you don't generate that much traffic and you want to answer a question like this, well, there's no reason you couldn't just grep your logs for it. So I actually wanted to show the code that we use for the computation timeouts because it tells a specific type of story, which is that as analysts, our programming tasks can't be that hard, because if it is, then it makes it difficult for us to answer the questions. So I'd like to show you the tools that we're using, because ultimately our tools need to be easy to use. So this script here is the computation timeouts MapReduce script, and the important lines are 12 through 9. How many people here are familiar with MapReduce? Just a show of hands. How many people are not familiar with MapReduce? Okay. So, so MapReduce is a technology for doing distributed computation. Typically, the way it works is you have, like in the example of Apache logs, the mapper will take one record at a time to each call of a map function. The map function will then yield a set of values, a key and a value pair. All keys that match end up at the same reducer with the list of values that were yielded in the mappers. So you can use that for collecting and for counting and for doing summation and stuff like that. So, so let's talk a little bit about what is happening here. Now, our MapReduce system has a little bit of magic happening in the background. For every record in the Apache log line is parsed and put into this value object. And this value object actually has several properties that allow us to very easily characterize it. Like, for instance, is it a Google bot, right? Or was the request from an internal IP? Because we don't care about Google bots and internal IPs. We care about users. So what our mapper is doing here is it's filtering. It's making sure that the request that we're currently looking at is not a Google bot and is not an internal IP. If those are good, then what we go and do is we go and parse the query string and we assign it to the parsed query property. Then we check, is the URI of the request the calculate timeout.jsp that we identified from before? If it is, then we check to see if compto is in the parsed query. And if compto is in the parsed query, we check to see that the value of it is true. So that's what's basically happening here. Then what we do is, if all of that's true, we yield the timestamp of the request realigned to the left edge of the day. So that becomes our key. And the value is 1. So what this will do now is the reducer is going to receive a list of 1s that correspond to each unique day. And our reducer, which is the Dumbo sum reducer, is going to add up that list of 1s. And so what you end up with, the result of this entire MapReduce process, is the count of computation timeouts per day. Remember, your BI process has to make sense for your business. If you don't use a lot of data, there's no need to write MapReduce code. You can do it using grep. You can do it anyhow you want. So just make sure that your tools are easy to use by your analysts. That's the most important point here. Step 3. Once you have created this data and you've put it into HDFS or your MySQL table, at this point we want to load it into Mathematica. So I went ahead and I ran this MapReduce code for the period starting on January 1st, 2012 until the end of April. And so this covers the period before and after the launch of Wolfram Alpha Pro. Now here we have some Mathematica code for loading that data into Mathematica. So here I'm just setting up some timestamps. The $epoch is the Unix timestamp. And then we have a start and a stop time, which corresponds to January 1st and May 1st. Then we open a link to Hadoop, and we set the location of the output of our MapReduce code, and then we go and we open the data. Now what's happening here is I'm actually just moving the timestamp because Mathematica uses a different timestamp from Unix. So I'm just readjusting it there, and I'm filtering it from the period start to end, start to stop. Now once I've loaded the data, I can now visualize it. So here we have a graph of the total number of computation timeouts per day. Now this chart isn't telling us anything. It's not telling us a story. All we know is that it has some sort of a profile. Now what we can see is that it has weekly periodicity, and it seems to have a seasonal trend. Now this chart down here is actually 2010 and 2011 traffic to our input page. And what's interesting to note is that it demonstrates that we do have a seasonal trend, a seasonal thing that repeats every year. Now what we want to do is we want to take that computation timeouts chart and we want to fix it. We want to remove the weekly periodicity and the seasonal trends. Now in this case here it's actually quite easy because all we have to do is divide the number of computation timeouts by the number of inputs. And so if we do that, our graph is now telling us a story. As we can see, the number of computation timeouts hasn't changed with respect to the number of inputs since the launch of Wolfram Alpha Pro. In fact, it's remained just over 10%. So what does this tell us? Well, it tells us that customers think they are experiencing more computation timeouts, but really, it's not a technical problem. It's a PR opportunity. It's a chance for Wolfram to reach out to our customers and to provide them with a better usage experience. So, up until now, our analysis has been relatively ad hoc. But for exploratory analysis, we need things like summary data, as we saw. I needed to use the input pages, the traffic to the input pages, in order to be able to normalize my chart. And so, it's important to create this summary data and have quick and easy access to it. So for us, we create traffic, popularities, unique users, and session type things as well, bounce rates, time on page, entry page, and exit page. And we compute all of this using Dumbo MapReduce. We then load all of the summary data into HBase, and everything is coordinated with our Jenkins tool, which is an open source tool and available from jenkinsci.org. Now, at this point, it's important for our data to be quick and easily accessible for Mathematica. And so we have a custom Mathematica package called website data. And website data allows us to do things like what is the traffic to the product's Mathematica page on the Wolfram domain? Or what are the search terms that rendered users from Google or other search engines to the Wolfram homepage? And so here you can see by asking website data for it, we can very quickly get back that Mathematica is the most popular search term. The point here is that the tools are easy to use. Now with quick and easy access to our data, it's now possible to institutionalize it and make this knowledge available to other people through dashboards and automated reports. Now the beauty of Mathematica is that we can put CDFs on our dashboard. And CDFs are interactive, which means you get a little bit more mileage out of your reports, and therefore fewer requests for reports. So I'd like to show you a demo dashboard that I've created for this talk. So here's our demo dashboard. Okay. So the first chart that we have here is what I like to call user engagement. User engagement compares the number of inputs and the number of unique users. It also has the ability to show a ratio between inputs and unique users. Now, right now this is just a GIF file, but it's a web page, and I can click on it and it will swap in a CDF version or not. Here we go. Downloading. Oh. I'm sorry, I don't actually have network connection. Or do I? Okay, that's working. Okay, sorry about that slight hiccup. Okay, so here we go. There we go. Yeah, we're good. Thanks. Sorry. So now we're looking at a CDF version of the same chart. And so here we can do things like compute the ratio between the number of inputs and the unique users. And what this shows us is effectively user engagement, because it allows us to see how many queries a user does when they visit Wolfram Alpha on average. And we can even add functionality to do moving averages so that we can smoothen out weekly periodicity. And so here we can see that in the summertime, Students do, on average, 5 queries per session, per day, that is. And then as the school year ramps up, they go up to 6. So there is a change in the usage patterns from summer to school term. Now the next chart that I'd like to show you is our predictive traffic analysis. This one here I thought was very interesting. We kind of stumbled upon it, but I hinted at it earlier. And the hint is that there does seem to be a correlation between the 2010 and the 2011 traffic patterns. In theory, it should be possible to build a model that predicts the next year's traffic. And so we made an attempt to do this. So this CDF here has the 2010. So let's first take a look at the raw data. The raw data has the weekly periodicity that needs to be removed. We smoothen it with a 7-day moving average. Now, once you've gotten here, we can create a model now of the traffic. And so we go and create a model for 2010 and 2011. And the model that we use is basically a least squares fit of the traffic to the 2 patterns that have been normalized between 0 and 1. We then do a linear extrapolation of the growth pattern. And there's going to be a workshop on this on Friday. So if you guys are interested in seeing how to actually do this in Mathematica, we'll be doing that on Friday. Now, the prediction is basically going to do the linear extrapolation of the growth pattern. And so what we can see here is what our predicted values are and what the actual traffic was for 2012. And the error is not that bad. Now this is telling us a story. This is telling us the story that our peak traffic is right at the beginning of December. So if your business saw a traffic pattern like this, then the best time to release a new product or to make an announcement is in December. That's what this is telling us. The last thing I'd like to show you guys is a new thing that we're working on. It's this ensemble session graph. It hasn't managed to tell us a story yet, but we're hoping that it will. The point here is that it's a process of exploration. So the idea here is that we have a graph, which is an ensemble of sessions. Now, a session is a clickstream, a set of, so when a user arrives at the home page and they start browsing your web page, it generates a clickstream, and we call this a session. This graph represents the set of sessions combined together to see how many users visited a node or how many users traversed a link. And so in this case, nodes are the URLs. The graph represents nodes that are URLs. And edges are links between URLs. When you click on a node, you filter the ensemble of graphs by the set of users that visited the URL. And when you click on the edge, you filter the ensemble by the set of users that followed the link. I thought that perhaps by doing this, we might be able to answer questions like what features of Wolfram Alpha Pro cause users to subscribe, or which pod of Facebook Analytics users do they interact with most. So far, we haven't managed to get it to tell that story because of some noise that we still have to remove, which is what we call normalization. But the point is, it's important to explore. So, in summary, we need to have easy-to-use tools because we want to make the life of our analysts easy. We want to empower them so that they can ask questions and answer them. When you have data, you need to normalize it in order to get a true understanding of the behavior of our customers. And we can do this by being intelligent about how we analyze our data. When our data tells a story, at that point we need to automate it in order to institutionalize that knowledge. We can never forget what we've learned. And we can increase the visibility of this knowledge using dashboards so that we always know where we are. And so, in closing, I'd like to quote Donald Rumsfeld, and Avinash Kaushik also quoted this in his talk. I thought it was really good. There are known knowns. These are things we know that we know. There are known unknowns. That is to say, there are things we know we don't know. But there are also unknown unknowns. There are things we don't know we don't know. We must aim to discover the unknown unknowns. In order to do that, we must explore our data in ways that we haven't thought of before. And we must empower our analysts with the tools of exploration. Thanks.